So this session is the Saga Continues Cloud Optimized Data Formats, and it's a session that's basically co-organized by the ESIP Cloud Computing Cluster. So I'll be talking more about the Cloud Computing Cluster as we sort of move along, but definitely, you know, there's so much meat here in this topic, which is why we've had so much excitement about both from speakers and from attendees. So definitely don't expect that we're going to obviously go in depth into all of these topics, but my hope is that we get a taste across some of the different implementations and also data formats that people are using to basically serve data on the cloud. We get a taste of that. We get to dig into some issues in some breakout sessions. And we actually come out with some, you know, you basically make a new connection or you learn a new thing. So definitely, you know, moving past this session, I'm hoping to get more of y'all involved in the cloud computing cluster so that we can use ESIP as a really unique space that's cross-cutting across industry, across agencies, across different types of stakeholders in this party. So like we have data providers, we have data engineers, we have scientists, and it goes across different organizations and agencies as well, as I said. So this is a really great space for us basically to start collaborating on these ideas that everybody's working towards. So my motivating introduction here, I'm just going to sort of reiterate it. It's written in the agenda doc, but you know, the cloud computing cluster is super excited for the next phase of cloud computing for earth sciences. In the past few years, a lot of new technologies such as ZAR, Pangeo, TileDB, COGS, EPT, Dask, and cloud storage for agency archives have gotten off the ground. And now we are really in the next phase of making these technologies operational and truly enabling everyday Earth data users to exercise those tools at scale. So the goals for this session, so most attendees will probably already know why move to the cloud. You know, cloud storage and computing enable greater access and use of Earth data on the cloud. And also I think, you know, Patrick Quinn, who's here with us, also highlighted, you know, how there's basically some existing really specific practical paradigms that the cloud is offering us in terms of using, you know, metadata and, you know, specific like actual implementations that all of these implementations are using, like HTTP, chunking via HTTP and direct file access, cloud native, et cetera. So cloud storage equalizes this data access and enables greater scales of insight. So hoping that everybody learn about a new tool or make a new connection, which will strengthen and reinforce a network and collaboration on cloud best practices, tools, and standards, which increases the value returned on investment. So I really like the idea that, you know, by using cloud, we can really get a strong ROI on all of the investments that we've made in putting data on the cloud and also the software that's being developed. So yeah, so we're going to go into some lightning talks. So getting a flavor of what people have been working on, and then we're going to basically talk about some different ideas for small group discussions and what we all want to sort of like really get out of this session. So those that we've already identified are cataloging, how to catalog ZAR stores, so stack items versus stack collections, how to share recipes and best practices using the cloud, and a demo of NOAA's environmental data record API and discussion. But I think there could be space for other small group discussions as well. So we'll talk about what those can be based on people's questions and interests, and organize into small groups. We'll then take a break, about a 15-minute break, before we actually jump into those small group discussions. And then I will ask that during the small group discussion, everybody takes time at the end to basically make sure that they capture their 3 takeaways, at least 3, you know, 3 to 5 maybe. And then we'll basically come back as a large group, and I'm going to have at least one person from each. I'm going to have one person from each group basically share the insights from another group. So we're going to sort of work together like that. Awesome. Okay. Any questions before we jump into the lightning talks? Cool. With that, I think, Trevor, you're up first.
All right. Let's see if we can get this screen sharing working appropriately. Are we seeing Google Slides?
Yes, thank you.
All right. All right. So my name is Trevor Skaggs. I'm with a company called Element 84, and this presentation is about exploring the advantages of cloud native, easily consumable, scalable formats for downstream scientific exploitation of point cloud data. It's a little bit of a wordy title. The reason that the title ends up being a little bit wordy has to do with the fact that this was a NASA initiated project. So we're working underneath the Access Grant with specific missions and objectives. And effectively, that was the mission that we had outlined. So overall objective was to perform a proof of concept, i.e. a small scale transformation of ISAT2 ATL06 product into a cloud native, easily scalable, usable, scalable, blah, blah, blah. So that work was performed under the NASA Access Grant Program that works towards increasing the scalability and accessibility of all large NASA satellite data sets. Who are we as an organization? Element 84 is a company that aims to help organizations and government agencies solve problems using remote sensing, life sciences, and transportation data sets. Similar to what Amy was alluding to as well, we're very much a cloud native organization. So we're aiming to use the cloud to help us solve these large scale problems and large scale data set issues. The three collaborators on this project, obviously myself, Trevor Skaggs, I'm a senior geospatial engineer. Matthew Hansen, who's also pretty familiar in this community, was a great assistance on this. And then lastly, Dan Pallone, who's the CTO and CEO of Element 84. We're going to do a quick little remedial class for some folks probably who aren't necessarily familiar with what a point cloud is, but a point clouds are just a collection of points that each represent a 3D shape or feature. Each point has an X, Y, and then a Z coordinate. And in some cases, you can attach additional attributes that may be useful later in the processing stream. Point clouds are most often created by methods such as photogrammetry or remote sensing. And again, remote sensing is just a way of collecting data of the Earth by use of satellites or aircrafts. In more recent time, we're also seeing drone and as well as stationary or terrestrial-based LiDAR is collecting a lot of remote sensing type data, giving us nice 3D models that we can then render in different formats. The schema that we decided to investigate as part of this project, we decided on Entwine point tiles, also known as EPT. A couple of the reasons that we chose to go with this as the solution we wanted to investigate, I have up here. Primarily, it's simple, flexible, octree-based storage format. So that makes reading and writing dynamic spatial queries against that data set quick and efficient. It's also encoding agnostic, meaning it doesn't necessarily care what format the data needs to be stored in. It just then does the organization on top of that. It also has a flexible attribute schema, which is going to be really important whenever you're working with these large scientific data sets, because there's a huge swath of additional attributes that come with the original data, and being able to plug and play that for the needs that you have for whatever your downstream consumer was an important aspect. And then lastly, it's lossless, meaning that we're retaining all of the data. We're not having any compression or any actual loss of the detail of the data. It's just nested in that octree. Some supporting organizations that actually do the work of supporting that format is Hobo Incorporated is responsible for kind of maintaining that open source library. And then if you are interested in checking out that product, you can check out Entwine.io. High level overview of the processing chain that we ended up using here. So I went out, I grabbed all the data to begin with. I started to sort it by cycle. And for ATL06, a cycle is basically their 3-month orbit cycle, which means in 3 months, it takes them about that long to get back to where they started. I took each of those 6 cycles, which is the amount of data that was available when I started this project. converted those to LAZ, which is a compressed point cloud format. Then I performed the EPT index on top of that. And then I ultimately uploaded that to an S3 bucket, which is a natively supported hosting mechanism for EPT, which is another huge advantage, is you don't need an additional infrastructure on top of like a server to host out the index at all. It is natively supported as an S3 endpoint. Give you an idea of what the project focused on. You can see here's the bounding box of where we were. There's the Southern Ocean. This is way, way down. Obviously, the data coming from ISAT2 probably makes you think that it's probably polar data in some capacity, and you'd be right. And so we ended up picking this shelf to see if we could pick out some interesting detail, as well as determine if we were able to see kind of some change over time potentially. You see the cycle, the starting and the end time of when the data was gathered for. So we ended up with about a year and a half or so of data. So there wasn't a huge amount of change in between that, but it was kind of the idea that if we were to continue to index this, we might be able to kind of glean that information out. And then, as I alluded to, we did gather that data across those first 6 cycles or 3-month blocks of ATL06 data. A little bit deep dive onto the piece I was discussing about the flexible attribute schema. So the top 4 categories here are definitely things that you would need for any point cloud. So the X, Y, and Z that I alluded to, as well as the GPS time that allows us to do that change monitoring across time. And then because there was a huge amount of additional data attached to the original ATL06 product, one of the main things that we ended up having to go through was meeting with the people who use this data on a regular basis and determine the additional attributes that they would want to have in this index. You can definitely index every value, but you're going to end up with a fairly large product. And since EPT is pretty efficient in indexing, we went for kind of a minimum viable product for the downstream consumer, and you could end up generating a couple of these depending on what your downstream consumer was looking like. And so the moral of that story is we ended up with some additional attributes that we are now able to filter against when we look at that index in a visualization tool. I have a quick note there at the bottom. We kind of did use the return number as a proxy, and I'll show you what that looks like. But basically, those are proxies for the beam ID, because each pass of this satellite ends up having 6 sensors, and it's 3 pairs that are gathering data. And so we wanted to be able to isolate either the left beam or the right beam, or specifically be able to isolate a specific beam. And again, for that change detection aspect. High level, what does it look like in raw, processed, and then ultimately indexed data? So the raw data itself was about 86 gigs. That converted right across 1,208 files. And because of the compression of LAZ and the fact that we dropped some of the attributes, we got it down to about 4.5. And then kind of importantly, you can see there is a slight increase when you index the raw files, or those raw LAZ files. There's a lot more files because of the octree, but you do end up with like a little bit of overhead. The larger your data set, the smaller the percentage of that overhead would end up being. So it's pretty significant when you're only looking at 1,200 files. But overall, you're seeing a giant decrease in total storage size compared to the raw data, which is a big component of why it's efficient and is able to be served out quickly. This is just a quick slide. I'm going to kind of go over it real quick of showing that EPT is hosted natively in S3. That endpoint, I believe at this point, the funding supporting that may have expired, so that may not work anymore at this point. But we're always looking for opportunities to get the data set back out there if people are interested in consuming it. Going to give you guys quick visualization. So on the left here, this is just looking at cycle 1. And then I colorized it by elevation. So you can really see that shelf standing out pretty strongly there. Over on the right, that's turning on all of the cycles. And so you can see we really start to paint a pretty good picture of that ice shelf with a fairly narrow band of data set. To be honest, ISAT2 doesn't have huge coverage over the world, so it's going to be much more valuable near those poles. But you can see you end up with a pretty good detailed data set once you combine all of those data into one visualization. Another interesting aspect I do like pointing out on the left, you can actually see where they had an issue with the orbit pathing. If you can see, I don't know if you guys can see my cursor, but you can actually see how this ends up getting wider. Their orbit was actually a little messed up, and they were able to correct it. And they actually went back through and filled that space back in later. Couple other examples of how you can colorize these based on the different attributes. So on the left here, now I'm basically colorizing it by which the original file was. So even by smashing these all together, by using EPT, you're able to leverage the ability to keep track of where the original file came from. And so you can even see right here, that's where they've decided to cut off that processing. So they've generated a new file. And you really are having that ability when you identify an issue to go back and look at that raw source data from that file ID. And then on the right, this one's a little bit harder to parse, but effectively this is showing you that level of detail that's being supplied by serving this out as a notch tree. So the red is a different level of detail than the green. And this is a poetry tool that's doing that visualization. And so what it allows you to kind of see is that it is dynamically serving out data as you need it.
Hey, Trevor, sorry, this is really cool, but I think we're running a little over time. Do you
Okay.
mind? Yeah.
Yeah, so I'll go to this. This is my last slide right here.
Awesome, thanks.
So the only thing I really wanted to cover is what else was new about EPT. So there's external HTTP-based support for EPT in QGIS directly. If you're an open source guy, that's a great tool. usgs.entwine.io. They've continued to do indexing of all of USGS's data. That's a great place to look and see how this index is and identify sources for data that you could use in a project. And then lastly, stat catalog for EPT is available. And that is all I have.
Awesome, cool to hear about that stat catalog. And I myself am an EPT fan, so thank you so much for that. That was really cool.
No problem.
Definitely would be interested in a session sometime just on point clouds if we don't get to it today.
Yeah.
So let's go to Joe from NASA JPL, going to talk about metadata raster format and GIBS. Joe, are you ready?
Yeah.
Cool, thanks.
So let me make this full screen. Is that coming across okay?
Yeah, looks great to me. Thanks.
All right, perfect. Yeah, so I am Joe Roberts. I'm from the NASA Jet Propulsion Laboratory. I'm going to talk about serving imagery in the cloud with the meta raster format. So I'm going to do a bit of somewhat of a deep dive into the meta raster format MRF, talk about its use by the Global Imagery Browser Services, or GIBS. So I'm one of the leads on GIBS, and that's the format we use. So I'm going to kind of explain why we're using GIBS over other formats like the cloud optimized GeoTIFF. So there will be a comparison with that format, and I'll also address some of the technology gaps that I see. So a little bit about MRF. So it's been around for some time. It originated from JPL in the early 2000s. So back before we had the cloud and AWS and all these nice cloud optimized formats. It was developed for efficient image tile pyramid generation and access to tiled imagery. So if you're not familiar with the concept of a tile pyramid, we can take a look at our infamous MRF cake here. So it's really a technique to take a really large raster data set, chop it into tiles at reduced resolution. So at the top of the pyramid, you have the lowest resolution image. And then as you increase the zoom level, you get more tiles with increasing resolution. So it's a pretty common technique that you see with—
Is that an actual cake? I'm sorry, that's amazing.
That is an actual cake that someone on our team made. Yes, it was consumed as well. So yeah, the nice thing about a tile pyramid is that it removes the need to store millions of image tiles as files. You could, in theory, just generate a bunch of PNG images and JPEGs and put them into on your file system into different directories. But then there's an issue of file management. You're possibly dealing with millions of files. And then there's also latency, opening and closing a bunch of files. So MRF is open source, is implemented in the Geospatial Data Abstraction Library, or GDAW, and by extension is supported in common GIS software that uses GDAW, such as ArcGIS and QGIS. So MRF is not just a single file, it's actually a data set that's split into 3 or more files. So the .mrf extension only refers to the XML file header. So it contains metadata such as the size of the imagery, the georeferencing information, and color palettes and so forth. there is an index file that contains a record of all the different tiles within that data set. So the data file itself is basically a pile of images in a variety of formats. So there's, it can be PNG, JPEG, TIFF, even a vector tile, even though the name is meta raster format, and LERC, which stands for the limited error raster compression. It's a compression technique developed from Esri that allows for really fast compression and decompression. So these all kind of map up to these different file extensions. So PNG maps to PPG, JPEG to PJG, and so forth. And when an MRF is built, it's basically just appending images to the end of this large data file. And then the index file contains a pointer to where that tile exists in the larger data file. So it contains the size of that image plus the offset within the larger data file. And that's how you are able to pull a tile from the larger MRF. Optionally, there is a .ox.xml file that's just output by GDAL that contains additional metadata information. Since MRF is already split into different files, you can actually put them on separate storage. So for example, you could put the index files on faster block storage, and this allows for really quick lookups. One of the things that we found is a lot of the performance constraints is based on where you're storing, what type of storage that you're using. So for instance, if you're using S3, there's additional latency versus using something like EFS, the Elastic File System on Amazon. So you can gain a little bit of performance back by using block storage for the index files. And the way that MRF reads work is through the HTTP range reads, similar to cloud optimized geotiffs and other formats, that you're only reading a single range of bytes from the file that's on the object storage. You do need a reader, a client that's aware of the index structure. It could be mathematically computed, and this allows for the quick look of the tiles. The structure of the index file matches that of the level row and column that you see in common tile services, such as WebMap tile service. So that translates nicely in that sense. Index files are sparse, which means that empty parts of the file don't consume disk space. Although one thing that we found out is that S3 doesn't support sparse files, so we don't really gain that benefit when we're using when we move to the cloud. If you're interested in sort of a deeper dive into MRF, there is this MRF user guide that's out on GitHub. Okay, so a little bit about NASA's global imagery browse services. So GIBS is a full resolution image archive for NASA's Earth Science data products. So it's really the sort of visualization service for NASA EOS. It's mostly known for being the backend of NASA Worldview. If you haven't seen Worldview before, please check this out. There's some really rich information in NASA Worldview. And so GIBS is not just the backend for Worldview, but it's also used by different web clients and applications. Kodak State of the Ocean Tools uses this, and other organizations such as NOAA uses imagery from GIBS as well, and many other people. So it's really a set of web services based on community standards. There's probably over 1,000 image products at this time. I'm not sure if we're over the 1,000 mark, but we're probably pretty close to it. A lot of the imagery is available within 3 to 5 hours of observation. So we have near real-time imagery that gets built on the fly. Everything is archived as MR files. That is our only image archive format, although technically there are shape files for some of the vector data sets. So that's not 100% true, I guess. MR files are generated as global mosaics from raster images. So we generate full global imagery, not just a granule or a swath, but the entire world is generated when we build out these MRF files. And we use standard map projections. the equal rectangular EPSG 4326 and Web Mercator, as well as polar stereographic north and south. So sort of at a glance, so GIBS gets imagery from different data providers, mostly the NASA DACs. So there's a fairly complex system in place that pulls imagery from the data providers. We pre-generate all the imagery as MRF. So we're sort of, we take every single data file and build an MRF version of it. That's really just the visualization or sort of the preview image of what the data looks like. And that gets stored on S3, and it's served out through a special server that's open source called On Earth, which uses standard OGC compliant web services. So this slide shows the main reasons why we use GIBS, or sorry, why GIBS uses MRF versus other formats. So it's really great for dealing with JPEG and plotted PNG raster imagery. In GIBS case, we're not dealing with multi-dimensional arrays of floating point data. We only care about the image tiles. So MRF does a good job of supporting PNGs as well as a mix JPEG and PNG format. So you could have both JPEG and PNG within the same raster imagery, and could also support Mapbox vector tiles. It's really good for generating global mosaics, and we standardize all the grid resolutions, as well as time resolution. So we generate daily imagery or monthly imagery and so forth. But the standard grid resolutions gives us the ability to, have every data set in 2 kilometer, 1 kilometer, 500 meters. So they're sort of at the consistent resolutions that can be used to be compared across different data sets. And number 3 sort of refers to our move to the cloud. So before we were in the cloud, we already had this huge archive of MRF imagery. So it didn't really make sense to move to another format when we already had this substantial archive. MRF also has the benefit of being really fast to read. Uses that index file that allows for fast range reads from S3. And MRF is also really fast to generate. So that's a pretty important consideration for data providers, or if you're having a service to generate tons and tons of imagery. So GIBS processes hundreds of products per day, and they need to be available as soon as possible. One nice thing about MRF is that you can actually, we call this MRF Insert, where since the index file is pre-allocated, you can update the data as it becomes available. So we don't need to wait for all the granules to exist to build a global mosaic. We can update that mosaic as soon as the granules are acquired. So this animation here shows a new product being built out throughout the day. So this is a Modus true color imagery. And as soon as a new granule comes in, it basically gets sort of pasted into the MRF and built as the day moves along. The other alternative is just to rebuild the entire raster file every time.
Hey,
and
Jeff,
that's yep.
sorry, we're running out of
We're
running out of time. I just want to make sure I give everybody enough time. Yeah, cool. Thank you.
So sorry about that. So MRF is very similar to COGS. So they both support image tiling overviews, get range requests, and GDAW. So a few differences. So COGS rather than an index file like MRF, it uses an image file directory. And one thing we found out is that there's sort of an additional step to build COGS because it reorganizes the regular GeoTIFF into a cloud optimized structure. Talked about the sparse index already for MRF, so I'm going to skip that. And I talked about MRF Insert already. So this was a nice thing about MRFs, is that you don't have to wait for the data to be available up front. I'm not sure if you could do that with COGS. So that was an important consideration for the GIBS team. So with COGS, you can have different various compression. MRFs also allow for PNG and LURC and also MVT. So we're really big on JPEG and PNGs. So that was pretty important. We didn't do a really deep dive into the performance, our own comparisons, but Esri has this really nice presentation that talks about the performance of MRF versus cloud optimized GeoTIFFs. COGS are much better known than MRFs. So there are many clients that can directly read COGS in cloud storage. With MRF, we need to actually serve out the data through a different server. So there's not a lot of things that have full native support for reading MRFs directly from cloud storage. So this is my last slide. So MRFs in the GIBS sense are really just an image representation or a preview of the original source data. So we're pre-generating a lot of the MRF files, but the cost of doing this is that we have additional processing and storage that gets consumed. So we've been doing a lot of research into generating imagery on demand and trying to do it as fast as pre-generating the imagery and serving out from a cache. For small granules, this isn't too bad because you're only dealing with a small area. But for global imagery, it gets a lot more difficult. And using things like GPU acceleration helps quite a bit, but that comes at a cost of cloud instances with GPU capabilities are pretty expensive. Another issue is the scaling of color values into different bins. If you're pre-generating the imagery, you're sort of stuck with your original binning of colors, so you can't change from linear to logarithmic. You could change the colors, but you can't change the different binning of the colors. So we're looking for technologies that can sort of do this really rapid visualization without pre-generating a bunch of imagery and storage. And a lot of the data, sits in storage and doesn't get used. So there's sort of an argument there on whether we can generate things on demand. So that's it for my discussion. So yeah, thank you for listening.
Awesome, thanks, Joe. I think there's definitely some questions I know from Sudhir and myself, but I definitely appreciate the deeper dive into MRF, and we can follow up about those offline or in a separate session, but definitely appreciate learning more about a format that's being used to power such a powerful tool like GIBS. So now I think we're going to hear from Charles Stern, who's going to tell us about another cloud optimized data format that's a lot newer. So ZAR and PanGeoForge, well, specifically PanGeoForge, which is not specific to ZAR, to be clear. So I will pass it off to Charles.
Thanks, Amy. So I am going to do something which I'm a little bit nervous to do, but I think is the right thing to do, which is try to do a sort of not live coding, but sort of a live demonstration of some code that's actually running. So I just have showing you here a Jupyter lab that's running on Binder. I just want to be transparent about what we're doing here. So we're starting off with just a couple cells of executed with some imports. And importantly, I've opened a Dask cluster that will come in later, but we're going to actually try to do a computation with Dask and see how that works on ZAR. So PanGeoForge is a sort of a toolkit of tools for data extraction, transformation, and loading from archival formats into cloud optimized formats. And I'm Charles Stern. I'm a data infrastructure engineer with Columbia's Lamont Doherty Earth Observatory. So we're going to use an actual data set for this example, and this is the Copernicus Marine Environment Sea Surface Altimetry data. There's a link if you look at these slides later to the source from that, which is a European Union mission there. So many of you may be familiar with getting data from some sort of an FTP server, and this is what the FTP index for that data looks like. You have a sort of a top level for this data set, a different directory for each year from 1993 through 2020, and then within that, a directory for each month, and then within that, a netcdf file for each day within that month. So over a span of 1993 to 2017, which is what we're going to look at, that is almost 9,000 files. That's a lot of files, of course. And I think we all know that the old way to handle this would be to start downloading them. The total data set is about 500 gigabytes. That would take, I think for my test, something close to 24 hours to download. And then once we've done that, the data are not necessarily well situated for computation. They're sitting on a hard drive somewhere. So there's a better way, and that is PangeoForge, and particularly this package called PangeoForge Recipes, which is sort of a sub toolkit within the broader PangeoForge ecosystem that provides logic for transforming a number of source files into a single consolidated ZAR store. So the core of PangeoForge Recipes is a recipe, and a recipe is basically just a Python file, so it could be called recipe.py or something else similar to that, which has an ability to see where all of these source files live on their FTP server, and also knows how to logically arrange them into the cohesive ZAR store. So I'm going to just flip over to a GitHub page here that I have the recipe we're actually using. And we're not going to necessarily go into huge detail here, but you will probably recognize some familiar things here. For example, the URL for the data is given, but it's given in sort of an abstracted way, where the dates can be substituted by variables. This is allowing us to sort of have a more generalized impression of where this data set lives, and some important things we'll see in a moment, for example, how to concatenate all the different files that we're going to get from this data set. So if we go back to our slides and we look and import this recipe, this is the Copernicus Marine Environment Sea Surface Altimetry recipe, and kind of just summarize the inputs, you can see here, this is sort of what the data looks like from the perspective of the recipe. This sort of hierarchical FTP server structure has been flattened into a list of all the files, and they've importantly each been given some sort of a concatenation key. So they're all listed out and with the order in which they go in. This is an obviously very simple example because everything's just being concatenated in one time dimension, but there's really no limit to how complicated your concatenation can be. You can, reorganize these files if you wanted to, for example, if they weren't in the right order to begin with. And importantly, you can also do merging operations. So if we had other data variables that we wanted to merge into the same time series, we could do that as well. So once you have this sort of a recipe file that I've just shown you, that can be built into a ZAR store. There's a few different ways and places to do that. But the first step is, to cache files to a cloud location, just as netcdf files from their source server that allows rapid access to them to then write a ZAR store to your target location, generally also some type of cloud bucket. And that ZAR store will be written according to the alignment logic, those concatenation keys we were just looking at, but also some sort of chunking logic. So the chunking is not necessarily one-to-one with the alignment. You may want to combine multiple input files into a single chunk. You may want to subset a single input file into many chunks. But generally, the target is that the ZAR kind of base unit, the ZAR components of the ZAR store will be between 50 and 100 megabytes. That makes them sort of more optimized for parallel computation with Dask, which we'll see in a moment. So this recipe has already been built. We're going to import it into the, load it into the notebook. And just to note, this is a 500 gigabyte full data set that has been loaded pretty much instantaneously, let alone forget the downloading. I've just loaded it and it's all here. And in my case, I actually said, I only want to look at this subset of the data called the sea level anomaly. So I've actually added some logic into my recipe. I'm going to look at here that has a process input step. And it says basically just drop any data that is not the sea level altimetry. So it's important, you don't have to go one-to-one with your source files. I've dropped all of these other data variables from our data array, from our ZAR store, which are not sea level altimetry, because that's what I want to look at. So taking a look here, this is our data set again. We notice that it has a single data variable, which is sea level altimetry. So we're going to do an example calculation quickly, and we're about to wrap up. Actually, this is the climactic moment that I'm so nervous may or may not work, but I think it will, because I ran it earlier today and it seems good. So we're going to calculate a time series of the global mean sea level based on this sea level altimetry data. And again, this is basically taking the mean of 73, almost 74 gigabytes of data. And we're going to see if we can do that in real time using Dask. So I'm just opening up the client dashboard here, and we'll see if it actually shows itself. And it does actually. And we're going to start this as sea level altimetry time series, taking the mean of sea level altimetry over the spatial extent, latitude and longitude, start that computation, and then come back up to this Dask dashboard. And those of you that are familiar with Dask and will know that what we're looking at here is Dask elastically scaling up a cluster of workers to handle this almost 74 gigabyte computation. And we're looking here at a task stream of each of the sort of sub computations within that graph being computed. This is basically showing us the estimate. So we're now, in the time I've been talking about, halfway through taking the mean of that of those sea level values from that 74 gigabyte array. Now about 3/4, and we're about to have done all of our analysis that, of course, we would not, had we used a download method, not even have been barely begun downloading the data. That's now complete, and we can plot that with matplotlib and look at this time series. Usually this is actually the fastest step, so we'll see how that comes out. So here we are, global mean sea level. This is from real measurements from the Copernicus Marine Environment Mission. This is actually showing the rolling annual mean increasing, of course, from about 1993 until 2017. And that was something we've done in real time. Not all of that was computed on the fly just now. So to wrap up, what can you do today with Pangeo Forge recipes? You can start working on a recipe. The docs link is here. I'll add the slides, by the way, into our shared Google Doc for this session. You can start working on a recipe. Look at the documentation, see if it works. If you need help with it, raise an issue on the staged recipes repo, which is where we're collecting recipes. And when you're happy with your recipe, you can add it as a pull request to that repo. And what that will do is add it to a queue to be built automatically when that infrastructure is ready. That's in process right now, that infrastructure. But in the meantime, you can also build it manually using a notebook. And if you get to that step, again, just at me, so to speak, on these repos, and I'll help you with that. And just the final slide, what's coming soon? Automated builds in what we're calling bakeries, which are going to be cloud workers that will handle the building of these ZAR stores automatically. And also related to the upcoming discussion that we'll have after the lightning talks in my group, is we're working on a stack catalog of all the available data sets that are built in this way. So my GitHub handle is in the top of these slides, which I'll add to the notes. And please feel free to reach out with any further questions.
Awesome, thanks, Charles. And yeah, thanks for also highlighting your breakout session. So that will be coming up in a little bit. And I think we should move on now to Stavros, who's going to talk about another exciting new format, TileDB. The originator of TileDB, right? The inventor.
Yeah, thank you, Amy, and thank you for having me here. This is a good opportunity for me to talk about this. I love the community. I don't come from the geospatial community. I'm a database person, but we have a lot of expertise in geospatial and several other domains. So I'm hoping to give you a little bit of an insight into the other domains as well. All right, so let me share my screen. Before delving into the details, a little bit about me. I am an engineer at heart. I created the original TileDB project. It was a research project when I was working in Intel Labs and MIT. I come from the database sector. I have a PhD in data management. I had a lot of exposure to geospatial applications, a lot of algorithms, and a lot of data structures from the geospatial domain. But back in 2017, we decided that there is a lot of value in what we built with TileDB, and we wanted to spin it out into a company, which has been operational for the past 4 years. We are 40 people now. We apply TileDB to many different verticals. Some examples are, of course, any kind of Earth observation, but also healthcare. And today I will tell you briefly that LiDAR, for example, is no different than genomics when it comes to format and data management. So instead of actually describing the TileDB format, we have a very powerful cloud optimized format, which is very, very general. We coin it as universal because we can capture pretty much everything, and I will tell you how in a bit. I wanted to touch upon on a little more thought-provoking subject here. I thought that's the perfect venue to do this so that I can spark a little bit of conversation. And the title of my presentation is Time to Depart from Formats, right? Instead of describing to you our format, I want to tell you that although it's super powerful, we are missing the big picture. So that's what this presentation is about. All right. So let me tell you the problems that I have seen with formats. Again, remember, I'm coming from the database domain. Geospatial was kind of new, like every single use case that I worked on. But then we had a lot of healthcare, a lot of telecom, a lot of time series, a lot of finance. So a lot of different applications. And it's the same story regardless of the domain. So everything I'm going to tell you here doesn't just apply to geospatial or Earth observation. It applies everywhere. So number one, let me touch upon a subgroup of problems which I call simple or single file formats, right? You can't imagine how many times when I was proposing the TileDB format, people were telling me, hey, but that's not a single file, and it's not an easy format. It's a little bit more involved. First of all, you already know that single file formats don't work on the cloud. The cloud object stores deal with immutable files, immutable objects, so you can't update them. And you need something different, more files. Also, something that you guys are not mentioning at all, but in big enterprises and more complicated applications, especially from the healthcare and the data warehousing domain, you can't get away without versioning and time traveling. Like you can't. You need versioning and time traveling built into the format. So you cannot have a single file for that. Regarding format specs, and when I say spec is when I hear people, yeah, we're going to define the format. We're not going to think about the implementation, just the format, and that's the spec. And everybody has to follow the spec, and you can create multiple engines. A format without an efficient engine is just not sufficient, guys. Most of the complexity and the magic is in the engineering of the engine. Okay, it doesn't matter how slick the format is, if you don't have parallel I/O, if you don't know the SDKs of the object stores and the little peculiarities around eventual consistency, how expensive it is to list objects on S3 and stuff like that, it's just not going to work. Okay, the engine is what requires most of the work, and building the engine, you realize that something in the format spec goes wrong because it doesn't work fast. So just the format spec alone is not enough. Another thing that everybody should bear in mind is that if you have if you have more than one engine, which is the format gatekeeper, the people that are deciding what goes in the spec, it can create a lot of mess because the users and the customers are coming back and they're saying, hey, I have this problem, fix it. You can't gather 100 people that have an opinion on the spec to change the spec fast enough for the customer and the user to enjoy the performance. So if you can have a community, but if you have more than one engines, once the format spec changes, and it will have to change, all the engines will have to change. So that creates a mess. And one more thing, because we're putting a lot of spotlight on the formats, the format and even the engine is just a very small piece of what the actual users and customers in the enterprise or even in the open source domain need. They need data management. Storage is just the beginning of it. And coming from databases, guys, I mean, if you saw the domain of databases like decades ago, nobody cared about the format. Did you care what format the database is in Oracle or IBM DB2? No, all you cared about was SQL. As long as both systems support SQL fast, it doesn't matter what format they're using. So maybe we should take this as a hint. And finally, format standards. And by standards, I mean, certain organizations that say that's the file format we're going to use indefinitely. And this rings a bell, I'm sure. Any format, even TileDB, can be great until it becomes obsolete. Because, for example, cloud happened, right? Immutability of the files, a beautiful, very popular format, which was single file, doesn't work. So we have to be a little bit careful about when we say, I'm going to adopt that format and only that format. So what to do instead, keeping track of the time as well. Let me see. So here's what we should do. We should build engines and APIs. This is how it works. First, we design the format. It can be open spec, that's fine. And our format is open spec, but we allow it to evolve in time. It should be very agile. Then we build a super powerful engine. And guys, build it in C++. Build it in C++ so that we can build a lot of APIs on top. Don't build it in Python. Don't build it in Julia. Build it in something that is super interoperable and super fast. I would suggest there is one format gatekeeper in terms of an engine. Build one engine and then adopt it and promote it within the community, build it within the community, doesn't matter. And make sure there's backward compatibility. The format should evolve fast. It doesn't matter how many releases a month, but there should be backward compatibility so that nothing breaks. Support numerous storage backends. We're talking about the cloud. What if there is NVMe down the road and something completely different? So that has to be abstracted. This IO layer, it has to be abstracted, and TileDB does abstract it. If there is RAM or something else down the road, that should adapt very, very fast. Then build as many language APIs as possible. Okay, I mean, I love Python, I love R, but I love also Java, I love C++. It should work on everything. And adopt zero copy techniques. There is a lot of magic there on how to do this. And then you can use those APIs to integrate with everything. Viewers, databases, I mean, SQL databases, and anything else like distributed computation frameworks like Dask and Spark, everything. It should work with everything. And optionally push down primitives. This is what databases do very well. They push computations like Polygon queries down to the storage, down to the engine. That's why it is important to focus on the engine. And then help define API standards, guys. Like gather and say, okay, we use this format and this format, both great. How about we talk to those guys to try and agree on a common format? Because then you can migrate from one to another faster if you want to, and you increase the competition. All right, so what are the benefits? No reinvention of the wheel. You don't build, all these AWS SDK range requests multiple times. Guys, you've built it in the previous presentations. Like we're doing it again and again. It's the same. It's the same thing again and again. Then we enable rapid format changes. There is an easy way to pivot from one engine to another. I'm not advocating monopolies here. Actually, the opposite. I'm doing the opposite. We will offer extreme interoperability. Once the API is kind of stable, you can integrate it with anything out there. And more competition. I'm all for it. I want to see what other technologies are out there, and I want to compete with them as long as there is a common framework that that will not affect the users. The users and customers should not be affected by what we do, guys, when we advance the technology. All right, just a few. Amy, do I have 1 more minute?
Yes, that would be great if you could wrap it up.
All right, 1 more minute, guys. So what is TileDB? We call it a universal database. And by universal, we mean that we cover everything. And we do, I mean, we actually do. We have users, customers. We work very closely with very different domains, which happen not to be different. That's what I'm saying. The secret sauce is this. Okay, multi-dimensional arrays, both dense and sparse. Guys, these two have 90% similarity in the code base. For example, this has an R tree, this doesn't. This can handle cogs and stack of cogs. This can handle LiDAR very nicely, right? These domains can be real numbers, no problem. They can be strings. It can cover genomics, it can cover LiDAR, it can cover time series, it can cover anything. And the code base is 90% the same. All right. And the way you build something more than the storage engine is that you have the backends at the bottom, any kind of front end at the top, then you have the engine at the bottom. So that's the format and the engine. It's over here. It's just a piece. And then you build the database features on top. And with that, you can build the whole picture. You can build viewers. You can build anything. But this part is the base. All right. Sorry about abusing the time. I'm done.
No, that's great. And I was actually regretting a little bit naming this cloud optimized data formats, because I definitely want to proselytize the idea that this is about building cloud optimized services and APIs. And I love your slide about, I loved the slide about API standards and best practices, and think that we should also sort of start to talk about and disseminate those ideas as well. So thank you for that. Let's go to Steve and Shane from NOAA about the environmental data retrieval API.
Hey everyone, I'm Shane Mill from the National Weather Service. Today we're discussing the environmental data retrieval API. Let me hide this. So what problem does the OGC EDR API help solve? As we've discussed here, the Saga continues. Data, more data, a lot of native data formats that are difficult to access. We need to help manage that data, have easy access to that data, and supply the user with more flexible ways to access that data as well. We have this ongoing data silo issue that's been discussed so far today. We have all these different formats and different systems creating these silos for data access. You're putting a pretty large burden on the user of the data to figure out how to access that data, how to process that data, how to fit that data into their clients, and so on. The EDR API helps break down those silos. It homogenizes and integrates the data into one backend data store that could help disseminate the data pretty easily. It provides a uniform internet interface and platform where disparate data format systems and sources are all integrated and combined into web accessible structured endpoints. Here's an overview of the EDR API. In the last discussion, we discussed a lot about these disparate formats. The EDR API is looking to abstract the user from the different formats and systems. We homogenize the data and just provide one interface that's web accessible that provides self-describing URLs, standardized and structured URLs consumable by any browser or HTTP protocol. We want schema support for different output formats, CRSs, interpolations, and etc. And really the means to the end here is a feature extraction from a sampled coverage. So you have the boatload of data. We really want just the user to be able to access the specific data that they need. How does the EDR API work? So the EDR API through a lens, it allows users to query and request a feature from meteorological shapes. So we have a position, multi-point, radius, area, cube, trajectories, and corridors. Obviously, this extends it outside the meteorology domain. It could certainly be applied to many geospatial use cases. So here are some examples of the feature extractions that we are going for. It also provides an a la carte service. Basically, changing to geometric shape queries enable us to get closer to the data. It no longer matters to the user where the data originated from or what format it originates in. The user really just wants the data as a feature, no extras. So interoperability through simplicity is the key here. This approach becomes a one-stop shop data service for users. So really getting under the hood here, and some of these technologies that were discussed so far. So for one of our data access and processing use cases, we're typically using X-ray, Dask, and ZAR. So X-ray essentially is a Python object that allows data to be organized in the form of dimensions, coordinates, and attributes on top of NumPy-like arrays. The labels, though, allow us to keep track of the metadata, and ultimately, we want to organize that data in a certain way. Dask is a flexible library for parallel computing in Python. 2 demos ago, that was an excellent demonstration of the use of Dask. And we're using a very similar approach on our backend processing as well. So we're using Dask to chunk the data, locate in that X-ray object to improve performance for data access. X-ray's use of Dask allows for lazy loading of data. So if you recall 2 demos ago, the immediate response is because of the lazy loading of data. You don't do computation until you need the specific data, but all the metadata can be loaded right away. So it's a really powerful tool here. And then we're using ZAR basically to implement the chunk, compressed, and dimensional indexed arrays, and we're storing that on an Amazon Lustre file system, but it provides a lot of flexibility to S3, any other locations are super flexible. So I know this diagram is very small here, but the EDR API under the hood. So in this example, we have GFS data, so weather model data. It comes in grid files. We concatenate that into X-ray dataset, and then we reorganize and bin into the collections of weather parameters by common dimensions. So this X-ray dataset becomes multiple X-ray datasets, and then we rechunk with Dask, and we store on the Lustre file system in the form of ZAR. Now, with that processing happening, now we have the ZAR backend containing all of these different collections. So the EDR API, when a user selects a collection, it selects one of these ZAR data stores. So already you're trimming down the amount of data that's being accessed. And then the EDR API is transforming that ZAR data store back into X-ray dataset object. And because it's lazily loaded, the performance is super quick, because if you're selecting a point or a point time series, only that data is being computed. And then the access from the API could be in the form of, NetCDF, JSON, cloud optimized GeoTIFF, and so on. So we have plugins to support different output formats from this X-ray dataset object. EDR specification doesn't necessarily limit you to how you implement the backend. So I'm talking a lot about a ZAR backend. So you could have a use case where you just put all of the data into a ZAR data store. That's fine. There's nothing in the EDR API specification that keeps you from doing that. We found, though, that if you organize the data by weather parameters with common dimensions, it really allows for efficient trimming and slicing of the data. So that's what we chose to do with our GFS use case. Moving forward, the EDR API has benefits for both users and data providers. So for users, it really lowers the bar of entry for the data. You're only accessing the API. You're not trying to figure out how to process data from an FTP server or those native file formats. It really provides easy access to the data. You don't need to pull huge data sets. You don't need to receive the data in formats you can't use. No longer need a multitude of tools, processes, or scripts, and fewer issues with new data requirements and new data emerging. So that last discussion was really good there. You could have a database on the back end as well. The EDR API really is just an abstraction layer from the backend data source. For providers, it provides a flexible and extensible framework for the data providers. The specification can be configured in cloud or on-premise. We're really focusing on in cloud. Right now, the EDR API approach results in consistent, streamlined, and less convoluted data ingest and dissemination process. It draws users closer to the data, and in the future, we will support PubSub. So what's really cool here is instead of hammering, FTP server, you could have a notification service in the future where the user of your data will be aware when that data is available instead of just loading up a queue of 404 errors. The global interest in EDR APIs gain momentum. So NASA JPL, USGS, Unidata, they all plan to have EDR API implementations in late 2021. And then this part, OGC API services, so EDR features, et cetera, and metadata API records could benefit the WMO's WISP program. That stack discussion there was interesting. I know API records and stack are figuring out the approach there, and that could definitely help the WMO's WISP program. Here's some more information regarding the EDR API, OGC blog, the OGC EDR API website. We have a standards working group GitHub page as well. And then at that GitHub page, we have different deployments. So the National Web Service is one deployment, the UK Met Office, Wuhan University in China. There's many different deployments that you could definitely check out if there's interest. And then we'll do a demo in the breakout session. So stay tuned for that. And that's all I have on my end.
Awesome, thanks, Shane. That keeps us a little bit on schedule. Yeah, so the EDR API, oh, I just lost my screen. The environmental data retrieval API got a lot of interest at the last ESIP cloud computing cluster session as something people might want to reuse or learn from in terms of building these interoperable, specifically like geospatial environmental data types of APIs. And it sounds like it's gained a lot of traction at NOAA. So I think definitely if you're interested in, sort of being involved in the discussion about standards for APIs and specs with respect to geospatial data and serving geospatial data in a cloud native way, consider joining that breakout session to sort of join that discussion. I think there's also some overlap with the OGC standards that are being developed there. Cool, awesome. So last but certainly not least, we have Aaron from LPDAC.
All right, so let me know if the screen's not showing.
Looks good to me.
So my name is Aaron Fries. I'm the science coordination lead for the NASA LPDAC, actually a contractor through USGS. And I'm here to talk about kind of the NASA DAC angle to the migration to the cloud, as well as kind of how we're trickling this information and bringing people into the cloud, specifically our user community. So many of you know Earth Data or NASA is transitioning to the cloud. They're moving their data, website services, applications into what we kind of call the Earth Data Cloud. This lives in the AWS cloud in US West 2. So if you're interested, that's where the data lies. Why are we doing this? Well, of course, it's to manage the large data volumes. This is a common plot showing kind of the growth of data volumes going into the future. And there's really it stops at 2025, but there's not really any indication that this is going to stop. There's new missions generating just as much volume. So we're in an age, right, of big data. Also, the variety of data it complicates things as well, and bringing that data all into a single kind of virtual archive will help us kind of interconnect across the DACs. From a local analysis standpoint, we want to overcome these bottlenecks that we're now experiencing with these large data volumes, and then also kind of try to process that data at scale, or whatever really scale you want to process that. You have that ability. And then also put it like the data, the authoritative data next to the compute. So we don't have these kind of dark repos or copies of data kind of laying around on hard drives or wherever. We have a single source of kind of truth for that data that everybody can start at. So NASA has been transitioning to the cloud. They have a number of other kind of flagship applications out there. CMR search for metadata. The Earth Data Search client is an online client for discovering, accessing, visualizing data from all the DACs. And then we have the Harmony, Earth Data Harmony, which is kind of a framework for consistent access patterns for data services that are produced by DACs, by ESDIS, and so that we can have almost like a common API to access all these services. LPDAC is moving to the cloud as well. We have plans and are currently kind of acting on those plans to migrate our on-prem cloud assets to the cloud, or on-prem assets to the cloud. We also have data that's already in the cloud in cloud-optimized geotiff format through the harmonized Landsat Sentinel data that's being processed by the impact group. HLS is actually the kind of the first collection that we have that is fully contained in the cloud. It's produced, it's stored, accessed through the cloud. And so all these assets are available, whether you're on-prem, in the cloud, free of charge. In the future, we'll be transitioning our application for extracting, exploring, analysis ready samples application to the cloud. This has been an application that's been developed by the LPDAC, has kind of expanded into what we like to call an enterprise tool, though it's not encompassing every data set within NASA. But we'll be kind of first phase will be kind of forklifting the code up into the cloud and making some changes to optimize and to make it useful in the cloud. And then phase 2 will be integrating in with kind of Earth Data Harmony as its back end, really, so that we can start constructing the workflows that we can use to extract data for our users. In my current position, I do a lot of kind of outreach and advocating for kind of the transition to the cloud. And what we're really kind of pushing for is moving from the download and analyze paradigm to this kind of analysis in place or data proximate paradigm where you're doing your data search, your access, your processing all in the cloud, and then you really only just pull out what you need, final product basically. So we're using a lot of best practices and guidances from different groups like Pangeo to kind of push for this future state. How are we at the LPDAC encouraging this transition? We have a pretty strong legacy of producing tutorials in Python using Jupyter and producing kind of these things called data prep scripts. Our tutorials are really kind of a teach a person to fish type mentality versus the data prep scripts that are kind of handing a person a fish. And so tutorials go kind of end-to-end data discovery, data access, analysis, outputs with a nice little narrative to go along with them versus the prep scripts, which are really kind of a clip and ship command line executable that our users can use to just get the data immediately, really. All of our tutorials, our scripts, our kind of outreach materials are on this link below. It's managed in a Gitbucket repository. We also have an effort with OpenScapes, which is kind of an organization dedicated to encouraging open, inclusive, data-driven, reproducible science. And I'll kind of touch on that a little bit toward the end. And so for me personally, these three components have made it really kind of attractive for scientists like me to enter into this cloud domain. What's made it kind of really easy is this, the Pangeo framework. So USGS has a Pangeo, what we call a Pangeo instance that makes it just super easy to run code, build code, and really dip your toe into doing analysis in the cloud. Having a cloud optimized data set like HLS also allows us to really kind of advocate for that option and show its power. And then stack metadata records, spatial temporal asset catalogs, I think is one of the coolest things that I've experienced in a year or two. And they're very powerful ways of searching for data. And I think they're going to be kind of a backbone of all services really going forward. So a little bit more on Stack from a NASA angle. NASA has an API called CMR Stack API. This allows you to really find assets that are both on-prem at this point and in the cloud. And we build tutorials that show you how to, or we have built a tutorial that shows you kind of how to traverse that Stack API and how to use the search capabilities to find areas that meet your area of interest, your time series interest, the bands that you're interested in. We have tutorials that show you how to access single files using ReoX array, hitting the HTTPS access point, and then also doing a little bit more and leveraging the cloud optimized nature of those data and showing how to clip a file and reduce that kind of network load of that file, showing the kind of differences in speed when it comes to, I'm interested in a couple fields. I don't want the entire file. So that's the examples show the kind of differences in the speed there. We have some examples of building time series with our COG data. And so we build some VRTs and read those into Xarray. These are kind of a little bit outdated because this is a very kind of fluid, very fast moving area. And so we'll take our time to update to the best practices and have those out to our user community as soon as we can. And then usually as an output for our tutorials, we demonstrate kind of a process. And in many cases, it's like a vegetation indices that we're calculating, something like EVI or NDVI. But we build a time series, show you how to visualize that from the Jupyter Notebook and show that output and saving it. NASA is also making the data directly accessible. So you can access the S3 buckets directly if you have a temporary credential. And so we have some examples of leveraging that temporary credential and accessing S3 rather than the HTTPS data. And very much the same kind of narrative, accessing single files, building individual time series, clipping the data, are all kind of in these materials that we're demonstrating. So back to the NASA OpenScapes framework kind of collaboration. We're really kind of trying to build a community and engage with our community to advocate for transitioning science workflows to the cloud. And so there's a number of us DACs who are contributing to this effort. And one of the big things right now that we're working toward is a cookbook. And so this will demonstrate, have a number of, say, chapters that show you how to do certain things with the cloud data assets that NASA has. Show you kind of the ins and outs, some how-tos of certain things, how to really kind of access, maybe even combine data from different DACs at some point, as well as full-on kind of workflow examples. So this is something that's under construction. We are still kind of framing it in some way as well. And so any kind of commenting with regards to what would be beneficial to put in something like that would be great. Moving forward, we're going to encourage the adoption of cloud optimized formats. In my position, we're kind of we have some say, not necessarily say, but we have some influence in how new missions use formats. And so we're going to continue to show the advantages of that, continue to create tutorials, but we're going to do this more with an eye toward the OpenScapes. How does this fit within our OpenScapes framework? Is there a way to kind of converge on what we've traditionally been doing and how we can satisfy OpenScapes as well? And then we're going to continue to engage with our community, reach out to not only our user community, but also, say, universities, do various workshops with them, and just continue to advocate for cloud and show them that it's not really that scary from a science perspective. And so that's all I got. Thank you.
Awesome. Okay, cool. So that's a great segue to talking about the breakout group. So what we're going to do now is basically just recap what the breakout groups are going to be. I think there's a couple of ideas that have just been added here. So can somebody raise their hand if they added those ideas and would be interested in help facilitating one or both of those, these could be grouped together as well. Those ideas were the data format, access libraries, best practices, streaming to from portions of data objects versus full memory extract and slicing.
That was me, Amy.
Oh, cool. So Rob, then
I can't be on both.
yeah. Okay, why don't we, here's what I would propose is that we keep the 4 that we have, because I think that what I would like to do is recap the 4 that we have and have Annie, if you don't mind staying in the main room to help people find rooms. And then, I'm sorry?
Oh, I just said you bet. And do you want me to, did you create those rooms earlier, Amy, or I could happily?
I'm just going to create one more room for Joe Roberts to answer any questions on MRF and GIBS.
Perfect.
So what we're going to do is we're going to take a break, but first I want to recap what the small group discussions are going to be so that you guys can sort of have a productive break if you want. You can also just go grab coffee and not think about anything. But if you want to sort of use the break to go grab your coffee, walk around the block and think about these topics and sort of what you want to get out of the session or specific questions you want to ask, you can use the break to do that. So we're going to take a probably 10-minute break. And once we're done with that break, everybody's going to join a breakout room and join a discussion and come up with some takeaways. So the first breakout room is going to be facilitated by Charles with note taker Rob. And Charles Stern is going to talk about cataloging czar stores, stack items, or stack collections. The discussion prompt is CETA and Microsoft's Planetary Computer have made different determinations on this as evidenced in this discourse thread, and there's a link there. PangeoForge is currently making a decision on this topic of stack items versus stack collections. We'd very much appreciate community input. So I know that this has been a topic that's been of interest for a while, so I definitely think that it would be an amazing outcome to maybe come to some conclusion or decision as part of this breakout group, and everybody would be interested to hear about that. Second topic is what Aaron just mentioned, is there's this cloud cookbook that the OpenScapes framework has been working on. It's also an idea that has been discussed within the ESIP cloud computing cluster of having basically some resources for people, some best practices on using the cloud, creating cloud archives, as well as how can people contribute to those cookbooks? How can people reuse examples? I think a lot of people really like using, notebooks as examples, or to see basically, showcases or what's the word? So when lessons learned, those types of things. So I think it would be great to have a discussion with Aaron, and I was going to join that as well. The prompt here is OpenScapes is an initiative to develop resources for data center operators to produce cloud optimized data access and showcase how to use it. What are the best ways for ESIP's cloud computing community to contribute to this effort? Should we have a separate but complementary notebook? How should users share examples? Third group is demo of Noah's EDR API and discussion. So that's going to be a deeper dive into the EDR API with Shane and Steve, and lead in a discussion about how it could be reusable or extendable outside of the Noah ecosystem, OGC stack. And then Joe has offered graciously to also host any questions on MRF or GIBS, or where GIBS might be going in the future. So with that, unless there's any questions.
Sudhir was raising his hand.
Hey, Amy, so that was a question to Annie. So all these sub sessions that will be going into group, those will also be recorded, right?
Well, I have the setting that we have for Zoom now is that only the host can record, but I can see if I could go into those breakout rooms or if the co-host, just check the setting to see if the co-host would be able to record. So I could try to make all so if you could add your name to the chat, if you will be the lead in one of the rooms, so I could make sure each room has a designated co-host.
Okay, yeah, that will be helpful because, all the sub discussions are, actually important. And so if one goes to the other ones, they will miss other ones. So if there's a recorded, that will be actually a good one to have.
So if you are a lead of a room, I heard Rob is going to be a lead. Amy is going to be a lead. Could you list off the other folks that are going to lead the?
Yeah, it would be myself and Aaron for the best practices using the cloud room.
Okay.
And then Charles and Rob Casey for cataloging czar stores.
Okay. All right.
And then Shane and Steve and Sudhir and Rich for Noah's EDR API and discussion. Rich Signal.
Which Steve Olson, I'm presuming.
Steve Olson.
Yes.
Yep. Okay. All right. I think I've made everyone a co-host that needs to be a co-host.
So Annie, that means when we start, we just need to press the record button. Is that what it is?
Let's test it. We have a break. If Amy, you're saying a 10-minute break right now?
Yeah, so why don't everybody join the rooms at 9:40 Pacific, 12:40 Eastern. Join rooms then, and we'll do the breakout let's do the breakout for 25 minutes and then reconvene in the main room at 5 afternoon Eastern.
Sounds good. All right.
So how does it work? So do you move?
So Amy, could you create the breakout? You could always recreate them if we're all going to come back in here, but could you create the breakout rooms and just go into one of them and then see if record is an option for you as a co-host in that room and then come back to the main room?
Yes, let's see.
Okay.
I actually need to figure out how to join this room.
If you hover over on the right next to the room's name, there's a join button.
Annie, I just wanted to add that I did just go to my breakout room and press record, and I can confirm that I had the record button available to me. So
awesome. Okay.
I'll be back when the session starts.
Sweet. Amy, did you see the record button available for you? All right. Awesome. So if you could just make sure we could prompt everyone who's leading the session to press record in their respective rooms. And I could broadcast that message to it looks like people are moving into rooms already.
Can't find a way to rename rooms once I've named them, unfortunately.
Once they've already been opened?
Yeah.
Yeah, I don't know. Let me see if I can do it on my end. Yeah, it doesn't seem like there is once they've been opened, you can rename them. I think they're just, the name is what it is.
I wanted to give Joe's room a better name.
Oh, the Joe Roberts.
It's like, that's very.
It tells people what it is.
Yeah.
There's not gonna be confusion as to what the room is.
Yeah.
Okay. So, but it's the ones that, just to make sure, it's like cataloging czar stores, cloud best practices, EDR, Joe Roberts. It's just those 4.
Yeah.
And then, okay, awesome. And then you should be able to, as a co-host, you'll be able to move in and out of those. So if you, well, just like, I guess you just did.
Yeah.
So, and the other co-host should as well. So I'm just going to, I'll broadcast the message now. Reminder for all co-hosts in the your session. And anyone that's on still, or I hope you're taking a break, but if you are on and need help getting into a breakout room and it's not obvious to you, the first instructions are just when you go to the breakout button and you go all the way to the right, kind of near it, it'll have the number of people in that room. If you hover over it, join should pop up. But if you're having a problem getting into that breakout room, let me know and I can put you in there myself. Yeah, maybe that's. Amy, just checking on the cataloging czar stores, is that one purely going to focus on czar or is it going to be more of a stack combo?
Oh, good question. I'm going to guess, so I think the goal would probably be to be more about stack like what stack should be all about for cloud optimized data stores.
Okay.
But if I had to guess, it could derail into questions about czar.
Gotcha.
Right.
Okay.
So I shouldn't say derail. I mean, those are all very good questions.
Veer.
Veer. Right. So like people are very, yeah, as I'm sure you know, people are very interested in how to create the stack catalogs for different cloud optimized data stores and formats, and those are. But I think what happens is like that's like the second question, and like the first question is still how do I create my czar store?
Yeah. Okay.
I'm gonna have a little bio break, so
Oh yeah, go for it.
be
Yep.
back.
Sorry, I interrupt you. Go, please go ahead. Hi, everyone. Welcome back. As you are coming into the main room. All the other rooms are going to get abruptly closed in about 8 seconds. Okay. There's the abrupt.
Not enough time, not enough time.
I know, never enough time. Well, this is where we have this, just like, join our ESIP cloud computing cluster.
Right, just like not enough time. Sorry,
Yeah,
sorry, our group discussions, folks. If you have more questions, please ask here, I guess. So.
So everybody would have been kicked back to the main room, right? So we should just go ahead and jump into our wrap up.
Yep, I guess so. Yeah, we've been kicked out.
Yeah. There's no waiting when people are kicked into the main session. You can just go right into it, which I guess is the so I think that we had sort of an abbreviated small group discussion session. So I'm going to change approaches a little bit and have the note takers either state themselves what the main takeaways are, or ask for, somebody else to state the main takeaways, but basically to give a summary of their small group discussion. So Rob, are you prepared to sort of share what you guys talked about in the ZAR stack?
Yeah, and Charles can always jump in too, because he and I were trying to come up with a summary of things. But
Nice.
one of the fundamental questions that came up was with ZAR stores, we compare this to the stack metadata, and it's like, how do we get these two to work well together? ZAR is going to be a situation where you could have many data sets in many different places. And stack kind of gives you this overall umbrella to be able to connect geospatial parameters to find those ZAR data sets. And I think one of the big takeaways is that there's a desire to have visibility on what we want to have for relationships at these various levels of search and discoverability. And then there's also a concern about how much visibility is there across the different ZAR data stores in terms of how things are organized. What's the dimensionality? What's the granularity of the data sets? You could be dealing with a very complex data store set underneath, and you want to be able to capture this at a high level in a standard way. Is there anything else, Charles, maybe you could fill in there?
Yeah, that's a great summary, Rob. And I would just add that one of the things that I got from the group was this very interesting sort of, like you were saying, the division of labor, because Stack is in many ways designed to provide metadata level access to data formats that don't have some of the functionality that ZAR metadata already has. So it's sort of trying to figure out what parts of Stack we want to use for discovery and how to make that as easy as possible. But then for a lot of the subsetting and other functionality that Stack might have for other data types actually will be handled at the ZAR level probably. So there's more to be said, and I think we'll definitely be interested to continue the conversation on the discourse thread that is linked in our subgroup issue. So thank you.
Nice. So go ahead.
Yeah, Charles, I think that I was just going to write a note in here because I think we now have 3 types of metadata that we're talking about, and they support 3 very different use cases. You said Stack, and we have the ZAR, which is like file layout. But ZAR metadata also has attributes for groups and attributes for data sets that can be embedded in that ZAR metadata. So that's sort of an interesting thing. And then there's what I would call scientific metadata, the more detailed stuff. And Jeff in his intake picture was getting some of that stuff in there, like standard names. Standard names are probably in the ZAR catalog as well, or the ZAR metadata. So I think Micah had the idea of a diagram to figure these things out, and I think that'll be super helpful.
Yeah, it definitely sounds like we could have another session on this, a deep dive in one of the cloud computing cluster sessions, to maybe either work on that diagram together, or if somebody takes a first pass, we could review it together. So if I understand correctly, then you guys are talking about leveraging the existing structure of the metadata, or like format of the metadata, to actually create the stack metadata itself. But then there would also be some additional scientific metadata that's sort of native to the ZAR store itself. Am I understanding that correctly?
Well, there's some file attributes, like either global attributes or variable attributes in the NetCDF model, make it into the ZAR metadata. But then there's something like some other more complete scientific metadata, like more data quality, things like ISO that have a lot more stuff that does scientific, that supports scientific understanding of the data rather than discovery or chunk grabbing.
Okay.
And that there's a link, I think that that's actually accessed through a link, which is in in the stack metadata.
Okay. Okay, cool. Any other quick questions before we move on to the cloud cookbook discussion? So I met with Aaron and a bunch of other folks, some good questions from Chris Linus and Dave Meyer about basically next steps for sharing best practices and using the cloud. So one of the specific initiatives that we talked about was OpenScapes, and basically how OpenScapes is a framework for the data centers, the NASA data centers, to basically share how to create and use cloud optimized data stores. So they're working on a cloud cookbook that will basically share best practices and some examples for how to do this. And they're interested in figuring out, getting more community input into the content and then also using that. So we talked about basically how we've already been able to find examples of how to work either through our networks and or through things like Pangio's discourse. So we talked a little bit about how to basically expand the reach or expand the practice that the Pangeo community has developed to basically share things like notebooks or best practices or answer questions on things like discourse. So we don't want, to the extent that we can, we don't want these different initiatives to work too much in silos. And I think one of the ideas that I had during the session was that, or that I heard also, was that we don't want to, we don't want to silo notebooks with specific organizations or communities, but make sure that they reach a broader community through either a larger platform like ESIP or Pangeo, but also making sure that we are, asking each other questions on public platforms like a discourse platform. Does anybody from the larger group have questions or things to add to that discussion about sharing cloud optimized best practices?
I think the recipe kind of approach, and it's a similar approach to the cookbook, which is being used in the OpenScapes idea. But I think that's an interesting thing that Charles was talking about, and
Yeah. Yeah, with Pangeo forage recipes, there is definitely a Pangeo forage recipes definitely have a similarity with notebooks. Like you have sort of like like you might have an example Pangeo forage recipe of how to convert a certain collection, like a Modus collection, into ZAR or COG, and you want to make that as reusable or shareable as possible, right? So not just specific to maybe the Pangeo forage recipe, but maybe make it into a notebook that shows more generally how to do it even outside of the Pangeo forage ecosystem, for example.
Amy, something I'm thinking about based on your comment, I had initially thought of the cookbook conversation as one around reproducibility and how do we make sure people have the right environment to run a notebook. But in fact, this discoverability question has a lot of overlap with our stack conversation. And I can imagine that maybe we would even want to include in our stack catalog some links to cookbook examples, because I do know that I think you're allowed to include arbitrary metadata in a stack catalog entry. So we could say for a given data set, there could be a search, an item subfield called, cookbook examples, and that could conceivably point to some of these examples if they use that data set.
Yeah, I think that there are at least 2 use cases of pointing to notebooks or examples within metadata. And one is at the outset, when you're actually creating the cloud optimized data store, you want to provide some sort of link in terms of like what you said, reproducibility, showcasing like data provenance, methodology. This becomes important for research, I think. But then the other side of things are, hey, here's the ZAR store that you just discovered, or here's the cloud optimized data store you just discovered. Here's an example of how to use it, or here's multiple examples for how to use it. Yes.
Yeah, let's think about including these links in, say, for instance, data site metadata, which is associated with the DOI for the data set, because then it gets into the PID graph, sort of the big picture PID graph infrastructure. And if people use your data in a paper, it gets hooked into that PID graph through Crossref. And so then you've got links to these recipes, which are in as sort of a type, almost maybe a type of object in the PID graph, which would be very interesting.
That's a good point, Ted.
Oh, go ahead.
Oh, and I was thinking also that, as a matter of keeping things reproducible for a data set, it might be something for a service to return a condensed version of the cookbook that basically is Python code. And so somebody could basically replay that code to reproduce a collection of the data set. And that can be bundled with the data.
We need to, don't we need to be able to reproduce the environment though to run the notebook? Like binder links do that, right? Like they actually could create the container so that you can actually run the notebook.
One of the things that I know that's come up with like the common metadata repository, NASA's common metadata repository, is these new concepts of software and algorithms, and they're still being developed. And there's probably something similar in OGC and probably discussed in Stack. But this idea that you do want to create all these interlinkings, right? So you'd say, okay, well, this is the algorithm that was used to develop this data set, and then here's the software that was used, and you create some sort of like research package.
Those are all great concepts.
I would just echo from the ZAR perspective what Rich just said about binder links. Rob, something I found that's interesting is that when you're accessing data on, let's say, Google Cloud or Amazon S3, I found that just rebuilding the environment, a Conda environment on your local machine doesn't actually necessarily guarantee that you can access the data from a cloud provider, because sometimes the environment requires sort of lower level, like environment variables set to be able to do that. So I think Binder is a really good example for being able to reproduce notebooks that access cloud data that can be pre-configured with the right environment variables to make sure that the data can be accessed.
Mm-hmm. That's a great description.
I wanted to add one other thing. In the newest version of the DataCite metadata schema that we just released a couple months ago, one of the things that got added is a resource type general of computational notebook. And the reason that we do that is for sort of exactly this idea of having a data set and having related identifiers that point to notebooks or recipes or things like that. And those things can also have DOIs, and they can also have, then they have a resource type general of computational notebook. So we're in the DataCite metadata schema, we're trying to build these useful metadata for describing these kinds of environments that include data sets and things that use those data sets to either for reproducibility or various things like that. So we're trying to sort of keep up there.
Cool. Yeah, so yeah, just to repeat reflect what I think I'm hearing is that, when we're going about creating these cloud optimized data assets, we want to establish these we want to share these best practices and also examples themselves of starting from, linking to the notebooks and the environments that we're using to create them, and making sure that those are reproducible using Binder Hub, but also making sure that those links are in the metadata themselves and the search APIs. And then making sure that people know how to use them through also linking in metadata, but also sharing as advocates, we should also be sharing here examples. So I'm just repeating for the group, but also for myself, I'm going to be taking some of these takeaways and putting them in the ESIP. There's like a summer 2021 ESIP meeting takeaways doc. So I definitely want to add some of this there, and probably also coordinate some follow-up computing cluster sessions, getting at some of the more nitty-gritty details, maybe even actually creating one of these metadata store example notebooks. Okay, cool. So I want to give a little bit of time too, obviously, to the last group. That was the NOAA's EDR API and discussion. So I don't know, Sudhir or Rich, if you want to summarize what you all talked about.
Sure. So basically, like here Shane sort of like give a quick demonstration because he didn't have enough time when he was presenting. So he gave a demonstration of API, how to consume the data service, right? And then how various data formats can be consumed. But it seems like there are a lot of opportunities based on my observation. Is like there are a lot of opportunity I see from this the OGC EDR API, because that API brings sort of like a lot of valuable capabilities to improve the data formats interoperability, right? Because a lot of the times that we were talking here, same thing about the data silos, right? So I see a lot of opportunities that the EDR API is bringing to the table, and it's a basically cool thing about that is it also supports like your backend analytics, but you still can have your own custom user interface you would like to build one, right? So there's an effort going on in whether service EDR API implementations with across the other agencies as well. So and I see like there are the EDR API standards, their working group, there are opportunity for collaboration as well. See, they're working on the OGC MetOcean as well. So there are quite a things going on in that. I see, and also talking to, again, I based on my limited experience with the stack, but I see there's opportunity to like if the API actually harnessing some of the capabilities of stack in that API. And I'll let Shane or anyone else to talk about. And Rich, if you want to add anything, if I missed.
Maybe
Yeah.
okay. Go ahead.
Okay, go ahead, Rich.
No, you go ahead.
Okay, yeah, just like the big takeaway I would like to say about the EDR API that was pretty consistent with a lot of the presentations is abstracting the users from those data silos. Like we can move on from that now. And I think, that discussion about Dask and the power behind Dask was really interesting. The discussion about the different file formats and how we should create APIs and engines instead, I thought that was really interesting too. So I think that's the direction that we're going. And I think there's a lot of overlap between these different groups.
Rich, you want to add?
Oh, I was just going to say that Shane, you can correct me if I'm wrong, but it seems like it's still sort of early days for that for the API. So there's a lot of opportunity for community involvement, as Sudhir mentioned.
Yeah, that's totally correct. The standard just became a standard, I believe, in March, but implementations are rather limited, and the implementations that are out there are definitely still prototypes. So yeah, if you want to get involved, definitely be in contact, and you could definitely, your opinions will definitely be heard. The more people who implement, the better we could test the standard. So, yep.
And Amy, so we have the notes put in the page number 12 for this one's some of the takeaways.
Awesome, thank you so much.
Yep.
I just want to see. Okay, so Matthew Biddle pointed to a new a session on fair research software. Okay, cool. So we're almost at time, and I did want to mention that we actually have our next ESIP cloud computing cluster session this Monday, the 26th. We don't have a slated speaker, but I think it would be a great opportunity for us to regroup again and discuss what we talked about and next steps. So one of the things that we have as a computing cluster as well is our charter, our cloud computing cluster plan for 2021. So I'm going to link to that in here. Hopefully that link works. Yeah, things we will do to fulfill our objectives is actually the specific link that I linked to, but I think we should use that time both to welcome, anybody that's here as new members and get introduced into what specific topics you guys are interested in, and talk about what we learned, and also talk about, there's definitely a lot of things that came up today that I think would be good for additional knowledge sharing sessions. So recapping what those would be and what the goals of those sessions would be. So I definitely invite anybody that's here to join that. And then I just want to take these last few minutes to really thank everybody for joining and participating. I know Annie and I were talking at the beginning of this that everybody is suffering from just a little bit of Zoom exhaustion. So I really appreciate everybody coming, and especially thank all the speakers for being here and putting so much thought and attention into this topic and this session. I really appreciate all of you, and also Annie for your support in this effort. So with that, Annie, is there anything else that I didn't cover that I should mention before we close?
Just to point everyone to the research showcase that's happening tonight. There's a lot of really great stuff, demos, etc., that are going to be there. It's open now, just if you want to peruse the resources that are over there, but it officially starts at 6 Eastern, I believe, if you want to talk to those folks who have submitted things. And I believe there's over 50 submissions from across ESIP. So really good stuff over there. And I'd also just encourage, since I heard I think early on, there was like this call for a Pointcloud session, to remember that, and remember that maybe for future talk topics, or even like a winter meeting session, because it seems like there was a nice call around that. So just highlighting that in the notes, since there did seem to be some enthusiasm there.
Yeah, I think a Pointcloud session, definitely sort of holistic metadata representation for science reproducibility session are two that I definitely hear a need for.
Other than that, that's it though.
All right, thanks everyone. Enjoy the rest of the summer session and your week.
Thanks,
Thank you.
everybody.
Bye.
Bye.
Thanks, everyone. Have a good day.
Thank you.